Gabriel have just introduced the benchmark suite and the design methodology of the LDBC benchmark suite. And based on the uh, benchmark design methodology, we proposed and we finally released the first version of the LDBC financial benchmark, which is based on the financial scenarios that we summarized from the intergroup scenarios and the sorry, and the other scenarios from the task force members from CreateLink and Nebula the scenarios. Okay, so first I would like to talk about the motivation of the FinBench. As Gable have just introduced, the SMB, the social network benchmark, is designed based on the social network scenarios. And when we turn to the financial scenarios, we found that there are some features on the data set and the queries and the workload, which embedded some the different choke points. And following the LDBC choke point driven benchmark design philosophy, uh, we are going to design a benchmark for evaluating the graph database systems in the financial scenarios with new choke points embedded, which I will elaborate them in the following slides. And the choke point is, is based on the financial data patterns and the workload patterns. And here I put a slide here to summarize the key features in the financial benchmark. The left is about the data set patterns. The power law degree distribution is common sense in the graph data set, and we found it also in the financial data set. And what's more is the max degree of the different scale on different scale. It will scale up when the data set scale up. And another feature here is agent multiplicity, which means let's think about a scenario we transfer from some account to another account. And in social network scenarios, we just know person know another person. He is a friend of another person, and they are just one edge between these two vertex pairs. And in financial scenarios, the agent multiplicity means we have two accounts, and the account A transfer monies to the account B, and we have multiple agents in the same vertex pairs. So that we call the agent multiplicity. And the second feature about the data set is the whole graph of the financial benchmark is a asymmetric dynamic temporal graph. Here I list three adjectives. Asymmetric is it's easy to understand. We transfer monies. It has directions, and the dynamic means all the entities, all the vertex and the edges in the graph data set, it was generated, and actually it's in the real systems it's all the dynamic. It's not like the SMB. We have some persons, have some countries. It's fixed. And another the last one is a temporal graph. Temporal graph means we have the time features. We have the time step field in the edges and more than one of the edge types. And the other thing to mention about the data set is the harbor vertex. It's actually we do some optimization on the harbor vertex to meet the latency requirements. And the right part is about the query workload, query and the workload patterns. First of the query workload patterns, we summarize the query named read-write queries, which I will expand it later. And most of the queries have a feature that you need to do the filtering based on the time window, because I just said the graph data set is a temporal graph. And another thing, based on the temporal window filtering, when you traverse on the graph to find the path, you need to do the recursive path filtering. It's based in the past, you need to when you hop to the next label, you need to filter the ages based on the last hop on the timestamp and the amount, the properties. And uh, the truncation is actually is a sampling method which we used to limit the exploration of the computation when traversing on the hypervertex. And the last one we proposed here is time-based query mix, which we proposed in the driver, which is the new feature in our second version. Okay, here is a schema of the FinBench dataset. This schema is summarized based on the synthetic dataset we profiled on the real system clusters. We have profiled about more than 10 business clusters to summarize the schemas. They are all match type of accounts, match type of the the account holders, which is the person and the companies here, and match type of many types of the mediums to sign into the account. And here we we propose this synthetic schema, which we have five vertex types and 12 edge types here. And you can see in the picture here, we have some dashed arrows. The dashed arrows means the edge is single edges, which does not have multiple edges between the same vertex pair. And the normal arrows here you can see is multiple edges. For example, you can see the account we have transfer and withdraw from account to account. This means there are multiple edges from the source account to the desktop account. And this schema means that the vertex are the entities in the financial systems, and the edges are actually the activities involving them. And in the first version of the FinBench dataset, we have implemented the power law distribution and the harbor vertex. As I have just mentioned, the degree increase with the scale. You can see we defined the in SFE scale factor 1, scale factor 1, the max degree is 1 kilo. And when the data scale up to the SF10, the max degree will scale up too. And the right side of this slide, we just put some profiling result on the SF.1 data set. We list the degree distribution and the number of accounts and the average degree and the average multiplicities. Here is the rewrite query pattern. Rewrite query, in SMB, in the LDBC benchmark suite, we have several query types. You will have the complex read query and some like simple read query, and we have some write operations. And the complex read queries in financial scenarios, we think it represents risk control strategies, which is actually running our real systems. And the redirect query is I named it. It's a transaction-webbed complex reads. It's used to we use a transaction to web the in the real system to web the risk control strategies. Take this workflow for example. From the beginning, the transaction begins, and at first here is transfer request raised by the users in the systems, and before the transfers were actually write into the embedded storage, we need to first check the status of the source account and the desk account. if all the source test accounts are they are white, they are not blocked. So we can go with workflow. If any account has been blocked, the transaction will abort and the transfer will fail. Uh, if uh, if if everything is okay, the workflow will go to we add a transfer age in a transaction and we run a risk control strategy. Here, the strategy here is to detect a triangle or a transfer cycle of a third-party account here. And if this risk control strategy is not detected, the status of the accounts are okay and the strategies are not hit, so we can commit the transaction and the transfer age will be finally write down to the storage. And if anything weird happens, like some accounts are blocked or some risk control strategies are detected, and the transaction will abort and we are turned to another transaction to mark the related account as blocked. That is workflow actually running the financial system. So we named it redirect query. You can see actually it was formed by the red queries here and complex query here and the simple risk here. Here's another feature about time window filtering. In the data set, in the schema, we have the timestamp field in the ages. And when we traversing the financial graph data sets, it will start from the queries are always vertex-centric, and we start from the starting node, and we would like to find the related account which has transfer relations from the source account in max in 3 hops at most. And we want to find how many mediums have signed in to the account which is related to the source account at 3 hops max. So these queries are bounded by the start time and the end time. It's like you when you transfer money or you find something in your like Alipay or WeChat Pay, you may always set a condition that I want to see my last month, all the transactions in the last month. That's the motivation here. And based on the time window filtering, here we have the recursive path filtering. When some money applied from the loan to the account, we want to trace the money where the money goes. So that's actually a path traversing problem. We start from the source const, and we want to see the money like a tree, to the root node, and finally go to the leaf node. And in each pass, you can see in each pass, we want to add some filters like in each pass, the timestamp order on the pass, the time order of the ages is ascending order. It means the timestamp of age 2 is lower than the timestamp of age 3. And regarding the amount ordered here, we suppose it to be descending order, right? And here's another several patterns in the temporal graph, which we detect the cycles and we detect the trees and the chains, which they are both the risk control strategies, and they are also bounded by the time window, and we may also have the recursive path filtering feature. And here's a truncation sort. In practice, the system optimization usually it cannot keep up with the increase of the workload complexity. So we in the practice we often truncate more important less important edges to avoid the truncation explosion, and it's actually sampling. Uh, from the source account here, when we traverse to the neighbors, if this vertex is a harbor vertex, then we find too many neighbors, and when we hop to the next hop, the complexity will explosion. So to control this explosion, we need to add a truncation. We define the two truncation truncation field, the truncation limit and the truncation order, to truncate the less important edges. The we truncate based on the timestamp descending. We truncate from the latest edges, and the limited is 5. So we grab the 5 latest timestamp. In timestamp, we grab the 5 edges, and we traverse to the next hop. This will control the complexity explosion. And the last one about the workload is time-biased query mix, which is different from SMB. In practice, the complex read, as I have mentioned, the complex read are the risk control strategies, and the simple read are the simple checks. So when we want run some risk control strategies, a time-biased function is designed to that complex read of longer time window is followed by more simple reads. In fact, it's when we run some risk control strategies, which the time window is bigger and longer, and we often do more simple checks here to keep the systems are secure. As I just talked about the dataset features and the workload features, here's a choke point we identified in the behind the features. The first choke point here in the storage is rather simple. It's temporal access locality. As I have just mentioned, if we need to handle such workload with temporal graph and temporal filters, if we can in the storage, we can sort the edges by temporal ID, which it provided temporal access locality to the query engines on the top of the storage engines. So it will the queries can access the edges in specific time windows. It's rather simple. And another choke point I identified here is language choke point. The recursive path filtering features in the query, which we cannot express this filtering in the current language like ISOGIC or Cipher. It's not an easy job to do that. One possible solutions here is we give an example here. This is an example which actually running in our system. Uh, uh, more than the standard language, we have brackets here, and the brackets here describe the filters that we are sliding on the path, and the path length, the sliding window, it's a sliding window, right? And the length of the sliding window is 2, and the sliding steps is 1, and when we sliding the windows on the path, you can see we add some filters here. In this window, we expected the time difference was within a delta, and we also add a termination condition that we expect the type of the test vertex is the people, and finally we return a path. Here is the extension we built to the current standard language, and this is a collaboration we developed with Professor Yin. And here's another example proposed by here's a yes, it's a work from the Professor Coe and Crowe. Sorry, it's from Professor Crowe. The truncation is also not supported by the current language standard. So Professor Crowe sees these features and he write a short paper to support this truncation. Here's a definition here. Here we can see the truncating. We add some truncating here, and we add the auto spec, and we yes, we add auto spec here, and the following the definitions are is in line with standard language, I think. Okay. Finally, it's our version plan. We released the first version of the FinBench in the last year, and all key features as I just mentioned is are all implemented. And in the first version, we support the data. We have generated the data set up to scale factor 10, which is 10 gigabytes. And the workload, we only have the transaction workload, including the 12 complex read queries, 6 simple read queries, and 19 write queries, and 3 read-write queries. And here we are working on the next version of the FinBench, which we have implemented the parameter creation, and we are now support the SF30 in the generator, and we are working on the 100 and 300. It's not a much easier job to scale up the data generator. We spend much of time in this data generator. And we are also working on a paper to describe the design, the methodology, and the choke points embedded in the FinBench. Hopefully, all these new data set generator and the paper will be announced in short. Okay. Finally, here's our developers and collaborations and the members in the task force. That's my talk. Thank you. Any questions?
Thanks, Xipeng, for the update on the financial benchmark. Yeah, I had two questions. One is about the truncation, and the other feature, like the ordering, the filtering. Yes.
Yes. Yeah.
Just, yeah, truncation, and the other one was the next one is called
Recursive path filtering.
yeah, yeah, exactly. So both of them, yeah, exactly, recursive path filtering and truncation. Both of them seem to be expressible, at least superficially, in SQL using window functions. Okay, so you would do a partition by order by limit or thing in SQL. So I mean, I'm a bit, yeah, surprised at specific truncation, because, okay, not sure. I think it would be nice maybe to have a if something is going to be proposed in GQL or something like that, maybe we try to make it as generic as possible. The other thing is, yeah, I'm not sure what you think about that. Don't you think? My question is rather, is recursive path filtering and truncation, aren't they very related? Would that not be covered by a single thing, like window functions in SQL?
Usually we use the sorry. Usually the recursive path filtering is the filters we use to traverse a path, and truncation is to limit the computation complexity, and this is also used when we traversing paths. So actually, in practice, we often use both of these features in a single query. And I think it's possible to solve this, to support these features in a window function. As I have just discussed with Gabor, that when we try to implement these features in with Neo4j, and we are going to match the edge list, and we pass edge list to a reduce function. And the reduce function, we pass the in a window function to filter the edge list and get the final result. But it works in the recursive path filtering. But we have not tried on this truncation. If I think about to support the truncation in the window function now, and I think we can define that window function. Likewise, it's possible to support these features with a window function.
All right. Okay. Second question, last question. So you say, yeah, it's indeed difficult to make a scalable data generator. That is a known fact. I suppose you're using something like Spark or something, some distributed framework for. So
Yes.
what is the underlying technology of your data generator?
Yes, we followed the new version of the SMB Spark generator,
Okay.
and we implemented the Figma generator in Spark.
Okay.
And most of the developers here are not very familiar with Spark generator, so
okay.
we spend much of time to learn it, and we profiling it and find the bottleneck and solve it.
Okay, I see. Okay.
Hi. Peter Fischer, University of Augsburg. My question is also regarding the temporal part. If I understand it correctly, you have point-in-time validity of the transaction, or is this an interval validity?
Actually, I miss. You mean the truncation or
No. If
transaction?
you look at the edges that have timestamps,
yes,
they have point-in-time timestamps, so they are valid at a point in time, or are they valid for a period of time?
It's actually the time point. I think.
Time point, okay.
Yes.
Because
when we write the time points in the ages, and we filter, we usually use time duration, like a time window.
Okay. The follow-up question would be, considering that you take this ordering among edges into account, have you looked at the semantics of temporal shortest path and so on? Because if you make the step to include that into the model, it might actually be worth in looking into the existing work on shortest path over temporal graphs or so, to then take the further leap and also consider these conditions, because the regular path have conditions like shortest path or so it might be worth looking into that.
Yes, as I just mentioned in the choke point of the recursive path filtering, here we the collaboration here we just propose the syntax, and beyond that we also do some optimization in this query execution.
Yeah.
And based on this syntax, we can name some the predicates to push down to the executions.
Yeah.
I think it's somehow like.
Yeah, but the syntax seems to be very much procedural at this point, so it might be worth looking into the literature at this point, where the specification of the path would be more declarative. Because here, and I think that matches what Peter's comment was also, that it's essentially simulating what SQL does, and it might be worth to take the next step and actually look that you describe how the path should look like and not how to implement it at the surface level.
Okay.
Yeah. But I'm very happy to discuss this offline.
Maybe we can discuss more about it, that work, and we can find
sure.
something more.